Welcome to the workshop. Today we want to take a look at limits at a real number and the definitions that we're going to be using for this idea. In another video we'll take a look at some theorems and then we'll also take a look at some examples. So beginning with the definitions, let's consider the definition of the limit at a real number. Alright, hopefully that wasn't too bad for you guys, me zooming through that. So the definition is, suppose there's some function from some domain, a subset of the real numbers, some function from D to R, and that A is an accumulation point of the domain D. We need it to be an accumulation point in order to take the limit there. So then the limit of f of x as x approaches A is some number L as long as we have this situation. Okay? So if we have for each epsilon greater than 0, so it's just some number greater than 0, for each one of those given, for each epsilon, we can find some delta, some other number, such that we're arbitrarily close to L, right? We're within epsilon of L whenever our values x are within delta of A. So when we're really close to A, then we're going to be really close to L. That's what this is trying to say. Of course, we need our values x to be in the domain of the function. So what does this look like for some function? Let's say that we have some function. It looks like a polynomial, maybe quadratic or something. And if we wanted to consider this point here, say that's our A value. If we wanted to take the limit as x approaches A, we can see here that we might want to say that it's right here. And that's where the function is. Okay? So maybe the function is defined there, and that's fantastic. But it doesn't have to be. It could be some open point where it's simply not defined there, or it could be defined to be something else. A lot of different possibilities. Okay? So for simplicity's sake, let's say that we have a nice function that, hey look, the function actually takes on that value. So let's call that value L. Okay? So as x becomes close to A, of course it's going to become close to that function value and take on that value L. Again, when it's defined and it's continuous, these things, when it has these things, then it's pretty easy. A nice visualization like this. And when we get our epsilon, what that does is it says that we're going to take some window, L minus epsilon, L plus epsilon, and we're going to try to take this. Okay. So this is our epsilon window around L, and we want to say that everything that is near A will fit within inside this epsilon window. The evaluations will. So if I find some window, then I can take these values. That might be a little bit high there. Up to there. Yeah, that looks pretty good. Alright, so this is a minus delta, and this is a plus delta. When I look inside this window, I'm getting values that are inside this window. Okay, so I'm concerning myself with this portion right here. And all of those values are between L plus epsilon and L minus epsilon. And as I shrink this window, I want to be able to shrink my delta appropriately, so that way I'm always getting things that are within this epsilon window. Okay, I need to be within this epsilon window whenever I'm within the delta window. If I cannot find such a delta, then the function is not considered to have this limit. Okay? So if we wanted to consider maybe a different example, we could have something along the lines of this, where we have an issue, right? There is a gap or a jump in our function. So if this were the case, if I were to choose, let's see here, let's say for some reason, let's just choose that guy right here. this could not be the limit, right? This value, let's call it A, could not be the limit because if I were to choose some epsilon window, I can't get a delta small enough to not include these points up here, which are outside of the epsilon window. So that could not be the limit. Similarly, we couldn't have this be the limit. So this is the definition of the limit of a function at a finite value and having a finite limit. All right. So next we want to consider the definition of a finite limit, or a limit at a real number, limit at a finite value, but having an infinite limit. So that's our next definition. All right, so this is our next definition and the last definition of the section. So we took a look at definition for the limit being finite, L, and here we want to look at the definition for the limit being infinite. So let f be some function with domain D and range in the real numbers. And let's suppose that A is an accumulation point of the domain D. Again, that's required in order for us to talk about the limit. Okay. All right. Let's see. To discuss that a little bit further, let me just briefly say that I can't have x values approaching A if A is not an accumulation point. For a sequence of x values to approach A, they need to become arbitrarily close to. So when I think about the value A, there needs to be some non-empty neighborhood around A for every epsilon, right? Every epsilon window about A has to be non-empty. So that's the definition of an accumulation point for A. So I have to be able to create a sequence of x values that can approach A that eventually are not just A itself. Because here we need that our x values are not actually A, right? We need it to be greater than 0. All right, so going over this definition, the limit of our function f of x as x approaches A is positive infinity if and only if, for every positive value, we can find a delta greater than 0 such that the function is larger than k whenever we're near A. So whenever we're within the deleted neighborhood of A, having size delta. Okay, so whenever we're within delta of A, but not actually equal to A itself. All right, the concern here, or one of the concerns, is that the function is quite likely not actually defined at A. That's the case whenever the limit is L and an infinite limit. Maybe not necessarily the case when the limit is L, but frequently the case here when we're looking at an infinite limit. And certainly we'll take a look at some examples of this in our next video. All right, so what does this really look like? Well, to keep things simple, let's draw a graph. Now I'm going to have two examples on here, though. So let's have our first one look like this, and our second one look like this. All right, so for the first example, let's say I take a k value right here, actually for both of them, k. Here, when I'm looking at this first function, we'll call it f. We can see that here, let's call this A. Near A, it goes off to infinity. Here's my A value. So whenever I can find some small window around A minus delta, A plus delta, whenever I can find that within that window, my values are beyond k, right? That hits here, so these are my values. They're all above k. Excellent. So we know that that limit is positive infinity. On the other hand, if we want to consider here, let's call this function g, then we might have values that are above k, but if we look at this value here, let's call it b. I drew this a little bit off, but it doesn't really matter. Whenever I look at some window around b, certainly I'll get some values which are above k. But when I look at the other side over here, I end up with values which are below k. All right. I could have even used an example that looked like this. Okay, it's not defined at all at b. Goes off to infinity on the left-hand side over here, but on the right-hand side, it's some constant value which is below k. This still would not have an infinite limit. All right, so this is what we can think of when we think of an infinite limit. All right, so that's all the definitions for this section. Limit at a real number, where the limit is a finite real number, and the limit at a real number, where that limit is positive infinity. We can make appropriate adaptations for negative infinity as well, and that may be necessary for some examples. But that's it. Those are our definitions. We'll see you guys soon with some theorems.